Okay, so let's start. In the last class, we were reviewing some basics of linear algebra, where we just recalled the definition of a vector space, correct? And we were looking at some examples. So, of course, we know that R to the k is a vector space, and it has dimension k. Now, on the other hand, if I consider the set of all n by n matrices, uh, is this a vector space? Yes, it is a vector space. And what is the dimension of this vector space? It is n squared, correct? And can you give me a basis for this particular vector space? Um, Permutation matrix? Correct. So one basis for the set of all n by n matrices is essentially, let me call this a I comma j, where all the entries are 0 except the I comma jth entry. So this would be the I comma jth entry. So this entry is 1, whereas all the remaining entries are 0. So this, using these matrices Aij, you can generate any n by n matrix just by taking a linear combination of Aij. And in fact, what should those linear combinations be? So if I give you an arbitrary matrix, say B, can you write that as a linear combination of these Aij's? How? What would be the coefficient? Correct. So if I have any matrix B with entries Bij, then I can simply write this as summation I comma j Bij times Ai comma j. Okay, so that's effectively only the ijth entry being 1 for this particular matrix means that I can write any matrix as a linear combination of the ijth entry of that particular matrix times this matrix Aij. Okay, so this forms a basis, and in fact all the Aij's are linearly independent, that you can easily verify. So this forms a basis, and how many matrices are there? There are n square. So the set of all n by n matrices forms a vector space, and this has dimension n square. Now what about, so dimension of, let me call this R n by n, this has dimension n square. Now let's consider the set of all n by n symmetric matrices. So all possible real matrices, real valued matrices, such that they're symmetric. Does this form a vector space? Okay, how do you argue? So does it satisfy all these properties? So addition is symmetric, addition is associative, the zero matrix is symmetric, so this property is satisfied. Does every matrix have an additive inverse? If A is a matrix, is minus A also, if A is a symmetric matrix, is minus A also a symmetric matrix? Yes, correct. And multiplication is associative, we have distributivity holding, and so on and so forth. Alright, so the set of all symmetric matrices indeed forms a vector space. In fact, it forms a vector subspace of the set of all n by n matrices. But what is the dimension of this particular subspace? I'll denote the set of all n by n symmetric matrices as Sn. Okay, so what would be the dimension? How do you get that?
In which exact diagonal entries are 1.
Diagonal entries are 1.
Exactly 1 entry in the diagonal is 1.
Oh, are you talking about a basis for? Okay.
and the remaining matrix is symmetric, so the upper diagonal can be constructed, and the lower diagonal is symmetric, so upper diagonal vectors are enough to denote that force.
Sure. So even if we take a step back, let's see how many, so to speak, degrees of freedom are there in the set of all n by n symmetric matrices. Right? What can you choose freely? You can choose any of the diagonal entries freely. Right? And once you fix all the elements above the diagonal, all the elements below the diagonal are automatically fixed. You can't change them anymore because they have to be symmetric. Correct? So every entry, you can freely choose any entry along the diagonal as well as above the diagonal. And the ones below the diagonal are frozen to you essentially. Correct? So how many entries can you really choose freely? Correct. So it is, if you go at it column wise, in the first column you can choose one entry, in the second column you can choose two entries, in the third column you can choose three entries, and so on. So it's 1 plus 2 plus 3 up to n, right? So those many entries can be chosen freely. And what does that amount to? So that's just n into n plus 1 by 2. Right? So the dimension of the set of all symmetric matrices is equal to n into n plus 1 by 2. Now if we had to construct a basis for this particular matrix, as you rightly pointed out, so I have n basis vectors which are obtained by taking one of the diagonal entries equal to 1 and the rest of them equal to 0, all other entries being equal to 0. So there are n such basis vectors. And for the off diagonal entries, I can take all the diagonal entries equal to 0 and one of these off diagonal entries equal to 0. Right? If I fix the I comma jth entry to be equal to 1, then since this should also be a symmetric matrix, the j comma ith entry should also be equal to 1 and all of the other entries are equal to 0. Correct? So if we had to sort of just take a 3 by 3 example or even a 2 by 2 example, can you list out all the basis vectors for S2? So 1, 0, 0, 0, this is one matrix. 0, 1, 0, 0, this is also a symmetric matrix. 0, 1, 1, 0, this is also a symmetric matrix. And you can see that you can generate any symmetric matrix as a linear combination of these. Correct? So any linear combination of these would take the form alpha, beta, beta, gamma. Correct? And any symmetric matrix can be written in this particular form. Right? Is that clear? Any questions? Okay. Now let's take another example. Consider the set of all polynomials of degree less than or equal to n and having real coefficients. Correct? So if I took n equal to 2, then this would be the set of all polynomials, which is, let me denote this Pn. If I take n equal to 2, then this would be the set of all a0 plus a1x plus a2x square, such that a0, a1, a2 are real. Does this form a vector space? Again, the easiest way is to check all the properties. Now, since we're looking at polynomial addition, obviously we don't have to worry about commutativity or associativity. Those are generally the easy ones to deal with. So that is not an issue. Firstly, is it closed? So if I add two polynomials, it always gives me another polynomial of degree less than or equal to n. If I multiply it by any real number, if I multiply the polynomial by a real number, all the coefficients get multiplied by the same value. That still remains a polynomial of degree less than or equal to n. The degree does not change. What else? What would be the zero vector? Yeah. Set all coefficients to be equal to 0, so that's the zero polynomial. What is the degree of this particular polynomial? The degree is equal to 0, it's still less than or equal to n. Okay, so that's still fine. Okay, what other properties do we need to check? Distributivity. Is that satisfied? So if I take some alpha times p1 of x plus p2 of x, is it equal to alpha p1 of x plus alpha p2 of x, and is alpha 1 plus alpha 2 times p of x equal to alpha 1 p of x plus alpha 2 p of x. So distributivity is satisfied. Anything else I need to check? Yeah, additive inverse. If I take a polynomial p of x and I just take the negative of all the coefficients, is that still a polynomial of degree less than or equal to n? Yes, it is. I have not imposed any other conditions on the coefficients of this polynomial. So the additive inverse also exists. If p of x is a polynomial, then minus p of x would just be its additive inverse. Correct? So is this a vector space? Yes. I don't hear a convincing yes. Are we missing any properties? Yeah? How many say it is a vector space? How many say it is not a vector space? What about the rest? It is a vector space, right? We've checked all the properties, all 7 of these properties, including closure. So it is indeed a vector space. And what is the dimension of this vector space? Yeah, n. So let's consider this particular example, P2. How many coefficients does it have? 3, right? So loosely speaking, there are 3 degrees of freedom. Again, that's just for intuition. So if you had to guess what the dimension is, what would it be? So this is a set, right? It's a well-defined set. So what is the dimension? The dimension should be one single number. Yeah? N plus 1, correct? And can you give me a basis for this particular vector space? So set one of the coefficients equal to 1 and all the other coefficients equal to 0. So for example, a basis for P2 would be simply the polynomials 1, x and x square, right? I can generate any polynomial of degree less than or equal to 2 but just by taking a linear combination of these. So this is indeed a vector space, and the dimension of this vector space is always equal to n plus 1. Okay. Now suppose I made a slight modification to this and said what about the set of all polynomials of degree exactly equal to n? Does that form a vector space? Let me just put on the question. So degree exactly equal to n, which means that the coefficient of x power n should be non-zero. Does not form a vector space. And why? Correct. So it violates a bunch of properties. One property is, well, if I add, firstly the zero vector does not belong to this set, correct? Because the coefficient of x power n cannot be equal to 0. So this does not form a vector space. What about the set of all complex numbers? Again, the underlying field is the real set of real numbers. Does this form a vector space? Yes, it does. And what is the dimension of this particular vector space? 2. Why? Yeah, correct. It's complex number. So okay, but again, all I need is you to provide me with a basis, right? Correct. So every complex number can be written as a plus I times b, where a and b are real numbers. So I can take the following basis, which is just 1 and I. Okay. Just by taking any real linear combination of these two, I can generate every complex number. Correct. So this forms a basis. The dimension of C, of course, here I'm assuming that the underlying field is the set of real numbers. So over the reals, the dimension of C is equal to 2. Okay, any questions? All right, so let's just do a quick review of some basic definitions. What is a subspace? If I give you a vector space V, then what is a subspace of V? Correct. So any subset, so if V is a vector space and S is any subset of V, if S is also a vector space, then S is called a subspace. Right? And if I had to test whether a particular subset is a subspace, do I need to test all the 7 properties? or is it enough to not test some of those properties?
Is float and present.
Correct. So if I need to test whether a particular set is a subspace or not, then all I need to test is whether it is closed under all possible linear combinations. If it is, then it will indeed form a vector space, a subspace. Right. So this is sufficient. So if we go back to earlier example of symmetric matrices, we know that set of all symmetric matrices is a subset of the set of all n by n matrices. So the only thing we needed to check over there was whether it was closed under linear combinations. Correct? All possible real linear combinations. We didn't have to check all the properties, all the 7 properties, because it's already a subset of the vector space of n by n matrices. Correct? Which one? Correct. But can you generate the additive identity by some linear combination? What about 0 times v? What should that be equal to? That should be equal to 0, right? So that's sufficient. Correct. So in fact, you can verify that just by, if this property is fully satisfied for all alpha 1, alpha 2 being real numbers, and for all v1, v2 in S, then that automatically forms a subspace. Right. So I'll leave that as an exercise to, if you've not seen it already, to check that all of these properties will also be satisfied. Again, the key point is that you already know that S is a subset of a vector space. If you don't know that, then this is not sufficient. Okay. Any other questions? Okay, so we've seen linear combinations. What do we mean by linear independence? If I give you a set of vectors, v1, v2 up to some vm, vectors from some vector space, when do you say that they are linearly independent? Okay, so when the following happens, so this is equal to the 0 vector if and only if all the ci's are equal to 0. So any non-zero linear combination of these vectors will always give you a non-zero vector. Correct. And if it is possible to find some non-zero linear combination of these vectors resulting in a 0 vector, then they're said to be linearly dependent. Correct. And what do you mean by the span of some subset of vectors? The set of all possible linear combinations of any subset of vectors is called the span. So the span of some set v1 through vm is simply the set of all vectors v that can be written as summation I equal to 1 to m alpha I vi for alpha I in R. Right? Set of all possible linear combinations is called the span. Does this form a vector space? Yes, it does form a vector space. And what would be the dimension of the span of some subset of m vectors? Yeah. Would it always be equal to m? It's less than or equal to m. More precisely, what would it be equal to? Correct. So the dimension of this particular of the span would be equal to the number of linearly independent vectors in this particular subset. Okay. So what is the basis of for a vector space? What is the basis? Correct. So any set of vectors which are linearly independent and span the space forms a basis for that particular vector space. Right. So V1 through Vn is a basis for some vector space if V1 through Vn are linearly independent and span the set, the subspace or vector space V. Right? And the size is the basis for a vector space unique? No, there can be multiple bases for a given vector space. Correct? But the number of basis vectors is always unique for a finite dimensional vector space, and this number is called the dimension. So the dimension of a vector space is basically equal to the cardinality of any basis for right. Okay. Now, given any matrix, let's say m by n matrix, you've seen that we can associate certain fundamental subspaces with this particular matrix. Right. So A is an m by n matrix. What are the four fundamental subspaces that are associated with this particular matrix? So the row space. And what is the row space? The span of the row vectors, right? So you take all possible linear combinations of the row vectors that forms a vector space, and that is called the row space. What is the dimension of the row space? The number of linearly independent rows, sometimes also called the row rank. Right? And what is the other fundamental subspace associated? The column space. So this is the span of the rows, and this is simply the span of the columns. The dimension of the column space, which is equal to the number of linearly independent columns, that's called the column rank or simply the rank. Okay, and that's because the row rank is always equal to the column rank. Okay, what is the other fundamental subspace? That is the right null space. Right, that we sometimes just refer to as the null space of A. This is the set of all vectors V in Rn such that A times V is equal to the 0 vector. The dimension of the right null space is sometimes called the nullity. What is the other? The left null space. Right, which is the set of all vectors in Rm such that, let's say, A transpose V equal to the 0 vector. Is there any relationship between the rank and the nullity? Correct. So the fundamental theorem that you've seen is that the rank of the matrix plus the nullity of A, this is equal to the number of columns. Right. So let's just do a very quick example. Let's compute the rank, nullity, the column space, and the right null space for this particular matrix. Yeah. Yes, please. The row rank is always equal to the column. Doesn't matter. Yes. But the dimension of the right null space is not equal to the dimension of the left null space. Okay. But the number of linearly independent rows is always equal to the number of linearly independent columns. If you've not seen a proof of that before, you can just go through any standard text in linear. Okay, so let's take this particular example. What is the rank of this particular matrix? The rank is equal to 1. So what should the nullity be equal to? 2 minus 1, that is equal to 1. Can you give me a basis for the column space? 1, 2. Essentially, the second column is just a multiple of the first column. So I can take any of these two columns as the column space. So it's the set of all alpha times 1, 2. And what about the right null space? Alpha times minus 2 comma 1. Are you sure? The right null space, remember. So this matrix times the vector should be equal to the 0 vector. Yeah, minus 3 comma 1. So minus 3 comma 1 is, if I take this matrix times minus 3 comma 1, I get the 0 vector. So that just gives me a basis. Okay, Let's move on. So how do you define the determinant of a matrix? Or what is the definition of a determinant that you have seen previously? Okay. Um, okay. So suppose I gave you a matrix and you have to compute the determinant. Or even more so, suppose I gave you, you had to write a program to compute the determinant of a particular matrix. Okay, so there are different ways of defining a determinant. One sort of the slightly more axiomatic way, you define the determinant to be a number which satisfies certain conditions, properties. But here is a more computational definition of a determinant that involves permutations. Okay, so suppose I give you some set, okay, maybe the set, let me say n. This n within square brackets essentially denotes 1, 2, 3 up to n. So any permutation on 1, 2, 3 up to n is basically a reordering of 1, 2, 3 up to n. Correct. So a permutation is essentially a reordering of these values. So if I take 1, 2, 3, then can you give me at least some possible reordering, some permutations of 1, 2, 3? Okay. 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1, 3, 1, 2. Are these all the possible permutations? So how many permutations are there for the first n integers? Yeah, n factorial. There are n factorial possible permutations. Correct. So in this case, 3 factorial is 6. So I have 6 different permutations. Correct. So each of these is a permutation, and I'll denote permutations by little sigma. Okay, so sigma is basically any bijective function from n to n. Normally. So basically any bijective map from 1 to 3 up to n to itself is a permutation. Just plain and simple. Okay. And you can see that the only possible bijections from 1 to 3 to itself is just this set. Alright. Okay, so this is a permutation, but these permutations have a rather surprising property. Something that I won't prove, but let's take any two permutations. Okay, you can generate this permutation, or you can go from one permutation to another by swapping pairs of elements at a time. Okay, so let's take an example. Let's take a permutation that takes 1, 2, 3, 4 and maps this to 4, 1, 3, 2. Okay. Now I could go from 1, 2, 3, 4 using pairwise swaps. What do I mean by that? Let's say that I swap 4 and 1. Okay. If I swap these two, then I get 4, 2, 3, 1. Okay, and I need to get 1, 3, 2. So let's say that I swap 1 and 2. So I get 4, 1, 3, 2, right? And I've got 4, 1, 3, 2. So how many pairwise swaps did I need? 2, correct? I could have done this in a different way, right? But let's try any other way. Let's take 1, 2, 3, 4. Okay, can you give me some other sequence of pairwise swaps to get to 4, 1, 3, 2? Take anything. Yeah. Okay, so let's take 2, 4. I get 1, 4, 3, 2. I'm basically exchanging these two. And now, which ones? 1 and 4, right? So 4, 1, 3, 2. Right? So again, two swaps. But I could potentially think of a more laborious procedure. So maybe I exchange 2 and 3. So I have 1, 2, 3, 4. Maybe I swap 2 and 3. I get 1, 3, 2, 4. Then maybe I exchange 1 and 4. I get 4, 3, 2, 1. Then maybe I exchange these two. So I get 4, 1, 2, 3. And then I swap these two. I get 4, 1, 3, 2. So how many pairwise swaps did I need? 1, 2, 3, and 4. 4. Correct? In fact, yeah, the point I'm trying to make is that the number of swaps is even. And you'll see that even if you try, you can never turn 1, 2, 3, 4 to 4, 1, 3, 2 using an odd number of swaps. So given any permutation, the number of pairwise swaps required is either odd or even. Okay, so if you can go from 1, 2, 3, 4 to any other permutation using an even number of swaps, then it's impossible to get to the same permutation using an odd number of pairwise swaps. And in fact, you can see why that it's the number of pairwise swaps. If it need not be unique, right? Because I could potentially take 1, 2, 3, 4, get to 4, 1, 3, 2, and then do two swaps. I could exchange 3, 2, and then once again exchange 3, 2, and get back the same permutation. So the number of pairwise swaps required is always odd or always even, and I'll define the sign of a permutation to be equal to +1 if it is even, and it's -1 if it is odd. Okay. So remember that sigma is a permutation. So it's a function from 1 to 3 up to n to 1 to 3 up to n. So using this, we can define the determinant of a matrix the determinant of a matrix A is simply equal to summation over all possible permutations of the sign of sigma times a1 comma sigma of 1, a2 comma sigma of 2 up to an comma sigma of n. Okay, again let's take the simple 2 by 2 case. All right, I have a matrix A which is equal to a11, a12, a21, a22. Right, the determinant of A, you already know a formula for this. That's equal to a11, a22 minus a12, a21. Right. So let's look at A. So it's a 2 by 2 matrix. So we need to consider all possible permutations of 1 comma 2. So what are the permutations, set of all permutations of 1 comma 2? One is the identity permutation, which just takes 1 comma 2 to itself. 1 comma 2. What is the other permutation? 2 comma 1. So there are only two possible permutations of 1 comma 2. And what is the sign of 1 comma 2? It's equal to plus 1, right? Because you need 0 pairwise swaps to get to 1 comma 2. What is the sign of 2 comma 1? It's equal to minus 1. Let's just apply this particular formula. What is the determinant of A? Which is equal to sign of 1 comma. So the first permutation is the identity permutation. It is plus 1 times a 1 comma sigma of 1, which is 1, times a 2 comma sigma of 2, which is equal to 2, plus the sign of 2 comma 1, which is minus 1, times a 1 comma sigma of 1, which is equal to 2, times a 2 comma sigma of 2, which is equal to 1. And you get back your original definition. A11. Sorry? So sigma is the permutation, right? So in this case, sigma of 1 is equal to 1 and sigma of 2 equals 2, right? So it's converting 1 comma 2 to 1 comma 2. So 1 is being mapped to 1 and 2 is being mapped to 2. In this case, for this particular permutation, 1 is being mapped to 2 and 2 is being mapped to 1. So sigma of 1 equal to 2 and sigma of 2 equals 1. Right? So going back to the 2 by 2 case, the determinant of A just boils down to your familiar expression of A11, A22 minus A21, A12. Correct? Let's quickly do the 3 by 3 case. A11, A12, A13, A21, A22, A23, A31, A32, A33. Again, let's list down all possible permutations. I have the identity permutation, which is 1, 2, 3. Let's take another permutation. 1, well, so I already have a list, right? Let me just reuse that. What is the sign of this? It's equal to plus 1. The sign of 1, 3, 2. I need one swap. I just exchange 2 and 3 to give me 3, 2. What is sign of 2, 1, 3? I just need to swap 1 and 2. So one swap is enough. What is the sign of 2, 3, 1? It's equal to plus 1, because I can first swap 1, I guess 3, 2 and then 1, 3. What is the sign of 3, 2, 1? Yeah, minus 1. Yes, so it's minus 1 because I just need to swap 1 and 3. What is the sign of 3, 1, 2? It's equal to plus 1. Right? And each of these corresponds to a product of certain terms. We'll see each of those. So this is, so let me plug it into the expression. So the determinant of A would be equal to, what is the first permutation? It is 1, 2, 3. So A11, A22, A33 plus minus 1 times A11, A23, A32. Right? In this particular case, sigma of 1 is equal to 1. It's equal to this particular entry. Sigma of 2 equals 3. And sigma of 3 equal to 2. In this particular example, sigma of 1 is equal to 2. It's equal to this entry. Sigma of 2 equals 1. And sigma of 3 equals 3. Okay, so these are the first two terms. Let me just write this as A11, A22, A33 minus A11, A23, A32. What is the next permutation? It is minus A12, A21, A33 plus A12, A23, A31 minus A13, A2, yeah, A22, A31 plus A13, A21, A3. Correct? Let me just this is equal to A11 times A22, A33 minus A23 A32 minus A12 times A21 A33 minus A23 A31 plus A13 times A21 A32 minus A22 A31. Correct? But what is this? This is exactly the formula for the 3 by 3 determinant that you've seen. Correct? So it boils down to the same thing. But now you have an explicit formula that you can calculate. Right? So in high school you would have seen the formula for a determinant in terms of minors and cofactors. Correct? This is essentially the same thing. Okay, but even in using this particular approach, what is the complexity required? What is the complexity of computing the determinant of an n by n matrix? How many operations do I have to perform? Yeah, so how many terms are there? There are n factorial terms. For each term, I need to compute n minus 1 products, right? I need to multiply n terms, right? So the computational complexity equals n factorial, whatever, it's some constant times n factorial times n, which is prohibitively large. So how does n factorial scale compared to, say, e to the power n? Which grows faster? N factorial, right? And why is that? Yes, but at what rate does n factorial scale compared to, say, e to the power n? Correct. So n factorial grows roughly like n to the power n, or n to the power some constant times n. So is there an easier way of computing the determinant of an n by n matrix? To do that, have you seen a simpler way of computing the determinant of an n by n matrix? Yeah. So what is the complexity of finding the determinant? Order of n cube. How? Okay, so let's see that. So suppose I give you a matrix A and I perform a sequence of row operations. What does each row operation correspond to? Can I represent a single row operation as a linear transformation of the matrix? Right? So every row operation is equivalent to left multiplying with a particular matrix. For instance, what about subtracting, let's take some row 2 minus some constant times row 1. What matrix does that correspond to? Yeah, so suppose I have the operation R2 becomes R2 minus some alpha times R1. You can take a simple 3 by 3 case if you want. Minus alpha 0 0 1 0 0 0 1. correct? So if I subtract a scaled row from another, what does the determinant of the matrix change? Suppose I perform this operation. So I have a matrix A. After performing,
Two one.
so suppose I have a matrix, I perform this row operation and get some matrix A prime. What can you say about the determinant of A prime? Take any matrix. Suppose I take 1, 2, 3, say 3, 1, 1, 2, 1, 2. Or let's make it even simpler. Zero, 0, 1. Yeah. Yeah. So again, let's do it using an example. So let's take this matrix. What is the determinant of this matrix? The determinant of this matrix would be equal to 1. Let's say I perform a row operation to convert this entry to be equal to 0. So I take a row 2 minus 3 times row 1. What would be the corresponding matrix? 1, 0, 0, 0, 1, 1, 2, 0, 1. Okay. What would be the determinant of this matrix? It's also equal to 1. So in general, again, this does not constitute a proof, but you can prove that the determinant does not change if you perform this kind of a row operation. Now, what if I scale one particular row? So basically, I take a matrix and I let R2 to be equal to alpha times R2. So R2 prime. Yeah, so what happens to the determinant of A prime? This would be alpha times the determinant of A, correct? And in fact, that's relatively easier to see using this particular formula, because if I scale one particular, let's say I scale the second row, right? That's like scaling the second entry in each product term by the same amount, alpha. I can take alpha outside and that just gives you a scaled version of the determinant. So scaling a particular row by some constant alpha also scales the determinant by the same constant alpha. What about exchanging two rows? Yeah. So if I say R2 prime is R1 and R1 prime is R2, then the determinant and in fact that's also, let's say, exchanging rows or exchanging columns, both of them both these kinds of operations just change the sign of the determinant. And that's also easy to see using this particular definition, because exchanging two columns would basically correspond to a pairwise swap, right? And so a pairwise swap would mean that the determinant changes. Okay, so now we know what each of these elementary row operations do to the matrix, right? So So suppose I took a matrix A and converted it to the row reduced echelon form. Right? So let me say that this is A prime. Okay. So what would be the determinant of A prime? Yeah. Okay, product of diagonal entries, but what would those be? So what do you mean by the row reduced echelon form of a particular matrix? What form does it take? Yeah, correct? Correct. So it's again we're dealing with square matrices here. So it's if the matrix has full rank, then the row reduced echelon form would be just be the identity. Correct. So what would be the determinant of A prime? That would be equal to 1 if the matrix is full rank and equal to 0 if it is not full rank. Right? And we'll assume for now that the matrix is full rank. Okay, so it's equal to 1 if A is full rank and equal to 0 otherwise. Alright. So in going from A to A prime, we did a number of row operations. Right? And all we need to do is keep track of what operations we did. So any kind of type 1 operations doesn't change the determinant, right? Any kind of type 2 operation essentially just scales the matrix, correct? So all we need to do is keep track of how many type 2 operations and how many type 3 operations we did. So suppose that I had C1, C2 up to Cm. I performed m number of type 2 operations and the corresponding coefficients I had to multiply with were C1, C2 up to Cm. Say, okay, these were what else? I need to keep track of how many type 3 operations I did, how many row swaps I had to do, correct? But just the number is enough, right? If I performed an even number of row swaps, then the determinant doesn't, the sign doesn't change. But if I performed an odd number of row swaps, then it does change. So it's minus 1 raised to number of the row swaps times the determinant of A, that would be equal to the determinant of A prime, correct? So what is the determinant of A equal to? The right hand side is equal to 1. So the determinant of A is simply equal to minus 1 raised to the number of swaps divided by C1, C2 up to Cn. Right? So let's see this with an example. Let's take an arbitrary matrix, say 1, 2, 3, 2, 1, 0, 0, 2, 0, 1, 0, 0, 0, 1, 2, 2, okay. what is the determinant of this particular matrix? Let's first compute using the formula. It is 2. And how did you get that? Yeah, you just take the second row. This is 1 minus 1 times 2 minus 4. That will just give me plus 2. Okay. Now let's convert this to whatever the echelon form. Say, what is the first operation you would do? So let's say that I exchange row 2 and row 3. I get 1, 2, 3, 2, 2, 1, 0, 0, 1. Okay. I perform another operation which is row 2 minus 2 times row 1. What do I get? 0 minus 2 minus 5, 0, 0, 1. Now let me say that I scale the second row. R2 prime equals minus 2 times minus half times R2. So I get 1, 2, 3, 0, 1, 5 by 2, 0, 0, 1. Now in fact I don't have to convert this to an identity matrix. What is the determinant of this particular matrix? It's equal to 1. So the determinant of any lower triangular or upper triangular matrix is simply equal to the product of the diagonal entities. Okay, great. So now that I have this, let's use this new approach of computing the determinant. How many row swaps did I have to do? I had to do one row swap, right? So the determinant equals minus 1 raised to the 1 divided by all the scaling factors. So this operation does not change the determinant. This operation does change, so it's minus 2. So minus half times the determinant would be equal to this. So this would be divided by minus half. So this would just be equal to plus. Okay. So in fact, this now gives us a much more computationally efficient way of computing the determinant. So computing the determinant is essentially just the complexity is the same as converting it to the echelon form. It's not any more harder than that. Any questions? So how many of you have seen this approach of computing the determinant before? Was this covered in your matrix theory course? How many of you have not seen this before? Okay, so now there's an efficient way of, so there are these different ways of viewing the determinant, right? So this is a computationally efficient way of computing the determinant, but in many applications, just knowing this particular approach, this is sometimes helpful, because it sometimes tells you something about the geometric structure of the determinant. And we will use that subsequently. Okay, great. So now let's jump to a different topic. Again, we're going through multiple topics very quickly just because this is ultimately just a refresher. Now suppose you're given a particular basis, you just want to convert that to a different basis, right? You want a new basis, a better basis. So typically the kinds of bases that we're interested in are orthonormal bases. And one way to get an orthonormal basis is to use Gram-Schmidt orthogonalization. So suppose you are given some set of vectors v1 through vm. How do you obtain an orthonormal basis from this? Yeah, so you take u1 to be equal to v1 by the norm of v1. So this ensures that u1 has no unit norm, correct? Or what's the next step? u2 equals v2, or let me call it u2 prime equals v2 minus the inner product of v2 with u1, right? Divided by yeah. What do you mean direction of u1? The inner product is a scalar, yes. Times u1. Correct. Not divided by. Okay. Next. Correct. So this vector may not have unit norm. So you take u2 to be equal to u2 prime divided by the norm of u2 prime. So what about u3 prime? So you take v3 minus the inner product with, so v3 comma u2 times u2 minus the inner product of v3 with u1 times u1. So the projection onto the subspace spanned by u1 and u2, and then you normalize, and so on, right? Because assuming that u2, u3, all of these are non-zero vectors. Okay, if v1 through vm were all linearly independent, then you would get an orthonormal basis of size m, right? A set of m orthonormal vectors. All right. Okay. Very good. So maybe this is a good point to stop. All right. So in the next class, we'll briefly look at eigenvalues and eigenvectors, and maybe properties of symmetric and positive semi-definite and positive definite matrices. So we'll try to wrap up our discussion on matrix theory as quickly as possible. Again, I'm not proving anything here. It's just a refresher. But then we'll see how to use this in convex analysis in the next week, in the classes starting from next week. Okay. Any questions?